stoichiometry with solutions. Okay. Well, stoichiometry means we got to get moles. Okay. So if you're given concentration, they tell you about the solution that you start with, because chemists mix solutions all the time because it makes reactions happen fast enough. Because we got to get the chemicals to touch each other, and the one place they can touch each other everywhere is in a solution. Right? So if I'm given concentration, you can use molarity to figure out moles. That concentration is going to be in molarity, and you can use that to figure out moles. And then you got moles of that chemical, you're ready to do stoichiometry. We started quite a few of our problems with moles at the beginning, right? So in essence, this is just like what do we do with ideal gases and stoichiometry. I don't get to use a conversion factor because I can't usually have a conversion factor for moles. So instead I have to solve a separate problem, get my moles, and then do the problem. Same kind of thing we did with gases. Okay? They ask you, what is the concentration of that other solution? By concentration, they usually mean molarity. In order to figure out the concentration, you would need to know the moles and the liters. So you do the stoichiometry to figure out the moles. And then once you got the moles, and you want molarity, you just need to divide by the volume of the solution. So you do all the things up to moles, stop, and then do another problem, just like using the ideal gas law when you're not at STP. Okay. They could ask you for the volume of a solution. How much of this am I going to need to add to react with so much of that? Once again, you need moles. So you can do a stoichiometry problem, stop at moles. That's why some of the times when we taught this, we started at moles or stopped at moles, was because I knew that on these kind of problems, that's where we're going to have to start and stop. Okay? And now I want molarity. And it's the, actually, I want liters. And it's the most commonly missed kinds of question. Okay? Because molarity is moles over liters. So what people want to do is they want to take and divide both sides by moles and get liters. But that doesn't work. That doesn't get you liters. That gets you 1 over liters. Okay? So what you need to do really is first get the liters off the bottom, multiply both sides, right? And then divide both sides by molarity. And you end up with liters equals moles over molarity, which is exactly opposite of what you expect it to be. Lots of people are going to do molarity over moles. But that won't work because your units will be inverse liters, which there's no such thing as an inverse liter. One over liter. Yeah. Okay, that's it. Nothing new. What we did yesterday, what we did last week, we're just putting together. Surprise, surprise. Like somebody told you at the beginning of the year that all we're going to do is just keep doing the same thing over and over again. Okay. If 45 milliliters of a 1.5 molar silver nitrate solution is added to excess KCl, how many grams of solid can form? Speaking of putting pieces together, there's a few pieces we have to put together here, like silver nitrate, potassium chloride. because I got to figure out what the solid's going to be. So I have to finish the equation first and then decide what on the other side won't dissolve in water. All these pieces fit together, folks. So what kind of reaction is it? Double replacement. So the Ag is going to end up next to the Cl, and the K is going to end up next to the NO3. Ag is always 1 plus, Cl is always 1 minus, so AgCl is correct. K is 1 plus, NO3 is 1 minus. That's okay. Now we have to decide which one or ones won't dissolve in water. Won't dissolve in water. Okay, so you got to go back to those solubility rules. Hopefully by now you've memorized the first one, which is if it's got an alkali metal in it, it's going to dissolve in water. So I know this one's going to be aqueous. Ag is not an alkali metal, so I look at the Cl. The rule for Cls are chlorides are soluble unless they're with silver, lead, or mercury. This one is with silver, so my solid is going to be silver chloride. Solid, S. So now I can take my, well, I got molarity, and I know that's moles over liters, but I need to change that into moles. So I need to multiply both sides by liters. So I get moles equals molarity times liters, which is 1.5 molar times 0.045 liters, because I got to move it over 3 times. And 1.5 times 0.045 is 0.068. And what units? Well, molarity is moles over liters, so I'm going to be left with just moles. So I got moles over liters times liters gets rid of liters. Okay. Now I've got moles. Now I can change what I'm talking about. So I'm going to start with the 0.068 moles of AgNO3, because that's what it was. I want to get rid of...
It's AgCl.
No, it's not. It's AgNO3.
Okay.
It's not AgCl yet. I've got to do the stoichiometry. It's not that yet. It will be, but I got to go from moles to moles. The coefficients of my equation are both 1s. Okay? And then I can go from moles of AgCl to grams of AgCl. 107.87 plus 35.45 is 143.32. 143.32 grams. And I push those buttons, and I get 9.8 grams of AgCl. Hugely different than what we've been doing? Same stuff, right? Okay. Yesterday I showed you the supersaturated sodium thiosulfate, and I said the only place I'd seen it was in the photographic process. So to make a black and white photograph, they would coat film or paper with silver bromide. When light hits silver bromide, it breaks the bond and leaves just silver behind. Then you take that paper, that film, and you rinse it with sodium thiosulfate, and it rinses off the silver and leaves the silver bromide, rinses off the silver bromide, which leaves just the silver behind. So where light hit, it turns dark. And that's how film, black and white film worked. Was they had a chemical that reacted with the silver bromide. Remember how silver chloride turned on our skins? Silver bromide does the same thing on the paper or on the film. Okay. Thiosulfate, the prefix thio, right? That thio means take off an oxygen, put on a sulfur instead. So this is called thiosulfate because sulfate is SO4. If I take off one of the O's and stick off an S instead, I get S2O3. That's why it's thiosulfate. Okay? It's another polyatomic ion because it ends in 8. But to the question, if you want to dissolve 0.225 grams of silver bromide, what volume of 0.0138 molars sodium thiosulfate should you use? Well, I got grams of silver bromide, but they asked me about thiosulfate. I need moles. Can I turn grams of silver bromide into moles? Yeah, I can. 0.225 grams of silver bromide. You want to get rid of grams of silver bromide and change it to moles of silver bromide. And 1 mole is 107.87 plus 79.9, 187.77. And then my balanced equation, I can go from moles of AgBr to moles of sodium thiosulfate, Na2SO3. And in my balanced equation, there's a 1 in front of AgR, there's a 2 in front of Na2SO3. Okay, so 0.225 divided by 187.77 times 2 is 0.00240 moles of Na2SO3. But we don't want moles, we want milliliters. So if molarity is moles over liters, then liters is moles over molarity. It's on the top of this side, it goes to the bottom. It's on the bottom of that side, it goes to the top. They switch places. So I've got 0.00240 moles divided by 0.0138 liters. And that is 0.174 liters, which is 174 milliliters. So see how it's just a stoichiometry problem, then a concentration problem. You're either going to start with molarity problem, or you're in with a molarity problem. Any problems? Well, let me tell you about your problems. They're on here. They're on this piece of paper. Please do not try to do them in the space between the numbers. You can use the bottom or the back if you want to, but please do not try to do them in the space between the numbers. Separate piece of paper is probably easier. You get less time flipping papers.